time one of the greatest mysteries of the universe. Could we ever travel through it? For centuries, this question has captured the minds of scientists and storytellers alike. From H.G. Wells' The Time Machine to the vast landscapes of Star Wars, the idea of traveling through time has become a staple in science fiction. But is it all just make-believe? Or are there real scientific principles at play? Welcome to our channel, your one station for all the news from space. Join us in today's video to find out if time travel is actually possible. Einstein turned our understanding of time on its head with his theories of special and general relativity. These theories demonstrated that time is not absolute, but rather a flexible dimension intertwined with space. Let's start with special relativity. Imagine you're standing on a platform watching a train whiz by. If someone were to ask you how fast the train was moving, you would look at how quickly it's passing by the fixed points on the platform, say the distance between two consecutive tiles. But what if you were on the train? Now the situation changes. You see, while you are in motion, what appears to be stationary is really moving along with you. In this case, it's the train. So, how do you measure speed now? That's where Einstein's theory of special relativity comes in. According to Einstein, the laws of physics are the same for all observers in uniform motion. Meaning, no matter whether you're standing on a platform or on a train, the laws of physics are the same. This led him to conclude that time is relative. It depends on your frame of reference. If you were on the train, your watch would seem to tick at the same rate as any other clock in your little world. But when compared to a clock on the platform, which is not moving relative to the track, your clock on the train would appear to be ticking more slowly. And this isn't just a perception thing. It's an actual physical phenomenon known as time dilation. So how much slower would a clock on a moving train tick compared to a stationary one? Here's the equation to calculate that. According to this equation, time slows down for objects moving at speeds close to the speed of light. The closer an object gets to the speed of light, the slower time passes for that object relative to a stationary observer. Now, let's step away from trains and talk about another form of gravitational time dilation. Einstein's theory of general relativity describes gravity not as a force, but as a curvature in spacetime caused by mass. Picture a bowling ball placed on a trampoline. It creates a dip in the fabric. Let's now roll a marble across the trampoline. Its path will curve towards the bowling ball, not because it's attracted to the bowling ball, but because the fabric of the trampoline has been warped. Similarly, according to general relativity, planets orbit stars, not because they're attracted to the stars, but because they're following the curves in space-time that have been warped by the star's gravity. But here's the twist. The deeper into this gravity well you go, the stronger the gravity becomes. So, near a black hole, where gravity is incredibly strong, time slows dramatically. The closer you get to a black hole, the slower time passes for you relative to an observer far away. Now, let's look at some real-world examples of these phenomena. In 1971, an experiment was conducted using atomic clocks on a plane to demonstrate that time dilation actually occurs. Atomic clocks are the most accurate clocks we have. They use the vibrations of atoms to measure time. So the clock on the fast-moving airplane ticked slower than the clock on Earth. Although the difference was tiny, it proved that special relativity works in the real world. There's also the story of astronaut Scott Kelly, who spent a year in space on the International Space Station. When he returned to Earth, he was only 1 minute younger than his identical twin brother Mark, who stayed on Earth. However, molecular analysis revealed that Scott had experienced some epigenetic changes due to time dilation during his journey. So even though they looked the same age, Scott is biologically a bit younger. And finally, GPS satellites orbiting Earth rely on time dilation. Because these satellites move fast and are far from Earth's gravity, time runs faster for them than for us on the ground. Without accounting for this time dilation, GPS systems would accumulate errors, leading to inaccurate positioning. With an understanding of how time can be manipulated, let's turn our attention to wormholes. Wormholes are hypothetical tunnels that connect to points in spacetime, allowing for the possibility of time travel. The concept of wormholes arises from Einstein's equations of general relativity, although they haven't been observed yet. To visualize a wormhole, imagine taking two separate points on a piece of paper and connecting them with a straight line. Then take that piece of paper and roll it into a cylinder. The two ends of the paper now represent different points in spacetime. A wormhole is like a shortcut through the cylinder, allowing you to travel between 2 points in spacetime more efficiently than going around the outside of the cylinder. But wait, things get even weirder. The inside of a wormhole is often referred to as a throat. And at the end of the throat, you have a singularity. Think of a black hole. The conditions inside a wormhole are extreme, involving intense gravity and potentially high levels of radiation. As you venture deeper into a wormhole, the gravitational forces become stronger and the radiation levels rise. Eventually, you reach the singularity, where gravity is so strong that nothing, not even light, can escape. If you want to delve deeper into the topic, check out our previous videos on black holes. We discussed their formation, life near them, and everything you need to know about these fascinating celestial objects. Some theories suggest that cosmic strings, which are hypothetical, one-dimensional defects in spacetime, could also facilitate time travel. These strings would have formed in the early universe and could have a significant impact on the structure of spacetime. If such structures exist, they could warp spacetime in ways that allow for time travel. Another interesting idea comes from closed time-like curves. This concept arises from solutions to Einstein's equations of general relativity. In some circumstances, these equations allow for the formation of closed loops in spacetime. These loops provide a theoretical framework for time travel, suggesting that it might be possible to move backward in time under certain conditions. However, time travel presents many challenges and paradoxes. One famous paradox is the grandfather paradox, which asks, what would happen if you went back in time and killed your grandfather before your father was born? If you eliminated your grandfather, how could your father exist to have children, including you, who then traveled back in time to kill the grandfather in the first place? This paradox highlights the logical issues that arise when considering the possibility of changing the past. Then there's the issue of causality. Traveling back in time could potentially disrupt the causal chain of events that led to the present. It could also require an enormous amount of energy to manipulate spacetime. Even if time travel were possible, the energy required to achieve it might be so great that it's practically impossible. Despite these challenges, the search for a better understanding of time travel continues. Experiments are being planned to further test the effects of relativity. And scientists are exploring how concepts from quantum mechanics might shed new light on this phenomenon. Who knows what the future holds? Maybe one day we'll uncover the secrets of time travel and rewrite our understanding of the universe. So the question we started with, is time travel possible? Well, based on our current understanding of physics, the answer seems to be yes. Time travel is theoretically possible through processes like time dilation, wormholes, cosmic strings, or closed time-like curves. However, there are numerous challenges and paradoxes associated with time travel that we currently don't have solutions for, so we continue to explore the mysteries of the cosmos. Who knows what new discoveries await us? Perhaps we've only begun to scratch the surface of understanding the true nature of time. What do you think? Is time travel truly impossible, or have we just not unlocked its secrets yet? Let us know in the comments below. That's all for today's video. If you enjoyed it, don't forget to hit the like button and subscribe to our channel for more exciting content. Your support helps us continue exploring the wonders of space and pushing the boundaries of human knowledge. Thanks for watching. We'll see you next time.